Okay, welcome to podcast number 2 regarding the scalar product, which can also be referred to as a dot product. Essentially, it's about trying to use vector means to find the angle between two vectors, and there will be some relationship as well with this so-called scalar product to perpendicularity when two vectors are crossing at exactly 90 degrees. You'll hear me interchangeably referring to the scalar product as also the dot product, because this so-called dot product, which will be sort of vector 1 dot vector 2, so v1 dot v2, will be appearing like a multiplication symbol, but it's actually referred to as a dot product. And there will be some issue of an angle, whether the angle is acute as directly given or whether it's obtuse. So we'll see that play out in the next couple of minutes. So let's find, classically using a scalar product, the angle between two vectors, and revisit what we saw in the previous podcast, where this angle theta, we used trigonometry means and the law of cosines to establish that it was 133 degrees, given that we knew the three lengths. So let's revisit this setting and get the same result using a so-called scalar product. Well, the background on the scalar product. So given any two vectors, generalized here as vector v and vector w, given that they cross to the point or they share the same tail, where the angle in between those two vectors is defined to be theta, there's something about v dot w equaling either this form here or v dot w equaling this form here. This one version of the scalar product simply says that the scalar product is the product of the lengths of these two vectors as multiplied by the cosine of the angle in between them. And the other form of the scalar product basically says, if you know the representational forms, we've seen numerically vectors like 3, 4, 12, 5, this kind of thing. If you simply know what these numbers are, multiply this guy times this guy and add that to the multiplication of this position times this position. So there's two different versions that will allow us to say, well, given each of these forms equal the dot product, then certainly they're equal to each other. So we can build a kind of a linkage between two representational forms involving vectors that flesh out this angle in between. At this level, there's no need to get into the background of why these are defined the way they are, why they actually work. But given that the area of knowledge mathematics is as tight and as secure as it is, these forms can be derived and even proven. Let's put it into application, however. So from the setting that we saw, we're still trying to flesh out the 133-degree angle there. So we would like to take a look at the dot product or scalar product between those two vectors there, namely vector AO and vector AB. Well, vector AO is just the opposite of vector OA, so that's just going to be -3, -4. That's how to get from A to O. And then AB, we already saw previously, is over 9 up 1. And so these two vectors regarding the dot product, if you will, or in other words, the way it's pronounced, AO dot AB, is simply the length of AO times the length of AB times the cosine of the angle in between them. That would be the first part of this definition. And the other part deals with just the multiplication numerically, or sort of arithmetically, of the two positions in play. So that would be -3 times 9. There it is right there. Add to that the -4 times the 1. And so this expression right here is just equating two different forms of the so-called scalar product. And the only unknown in here is this angle. So a little bit of arithmetic. Add these two together and get -31. Divide this under, right, root 582. And then do inverse cosine of both sides, and you'll flesh out the same 133-degree angle, not surprisingly, because math is pretty tight, once again, as an area of knowledge. Notice that this approach gave us directly, as it turns out, that acute angle. It is possible that if you were to extend that, that you can also be talking about the acute angle between two vectors. And so sometimes this method will give you directly the acute angle, and if that's what's asked for, you're already good to go. Possibly if it gives you, as it did in this case, the obtuse angle, then 180 degrees minus that would be the acute angle representing the angle between the two vectors. So there's always going to be two possibilities in play. You just have to be careful which one you're actually required to answer the question. Let's move it to 3 space. So let's say we're given position vectors of A and B respectively that look like this with the ijk form. I find the ijk form to be sort of superfluous in terms of just having to write ij and k too often, and especially in more complex settings. So if we're going to find the angle between these two vectors, let's just look at -1, 2, and 2, use the column vector form, and the 2, -3, 6, that column vector form. So apparently the scalar product between these two vectors, namely a dot b, is going to be the length of a times the length of b times the cosine of the angle between those two, and the addition separately of each of these 3 slots respectively being multiplied. So looking at that quite specifically in terms of how does one best determine the length of that vector in 3 space? Well, it's no more than just the x squared plus the y squared plus the z squared square rooted, if you will. Multiply that by the length of this guy here, similarly, times the cosine of the angle between them. That's the one form of the scalar product, and the other form just is really almost like the fun, easy arithmetic form, -1 times 2 plus 2 times -3 plus 2 times 6. Again, the only unknown in play is the theta angle, and so play out what you've got. That's just going to be 3 times 7, better known as 21, divided under, and take inverse cosine of both sides. We're talking about 79.0 degrees. If you're interested, in terms of these two vectors in space, how would you represent getting as a position vector, which of course has to be anchored at the origin, -1, 2, 2? Well, that would say go over -1, go up 2, come out 2. So A's head relative to its tail is right there. And then how would you represent B? Well, that would say go over 2, drop down 3, come out 6. That's a decent representation of what that vector would look like. And so the claim would be indicated in red here. The angle between those two vectors would be 79.0 degrees. That's the idea. So a fact is, because the scalar product is a function of cosine of an angle, we know from previous learning that the cosine of 90 degrees, whether it's in degree form or in radian form, is actually equal to 0. So if two vectors are coming in at 90-degree angles, namely if they're perpendicular, then the dot product would have to be 0, because that's the nature of what would happen here, regardless of their lengths. Cosine of 90, being 0, would 0 the whole thing out. So let's build on that in a rather abstract setting where you're given vector v and vector w looking like what you see here. Let's get the addition of those two vectors. Let's get the subtraction of one vector from the other. And then let's find the unknown value x, given that those two newly created vectors are in fact perpendicular to one another. So the addition of them is pretty straightforward. You're just adding x pieces, y pieces, and z pieces. And I mean x, y, and z very generally, because you can see the unknown in this setting is purely x. So the addition of these respectively are right here. So there's the vector that represents the addition of those two, and the vector representing the subtraction of w from v, x minus 2, there it is, 2 plus x, there it is, negative x plus 3, there it is. So now I have actually these two vectors, and the given condition is that the vector representing the sum, namely this one, is perpendicular to the vector representing the difference. And so if that's the case, then the dot product between these two vectors has to be 0. So this looks rather menacing notationally, but there's nothing really challenging going on here. It's just saying that a dot product has to be 0 because you're coming in at 90 degrees and cosine of 90 is 0. And then there's two different forms of the dot product that could be in play. And the form that just basically says, okay, I have one vector dot another, it's the multiplication of these two added to the multiplication of these two added to the multiplication of these two. That has to be 0 because that's the form that we saw previously in terms of those sort of 3 arithmetic levels matching up and summing up to be whatever. So careful algebra, collecting of like terms, you should be able to quickly see that this reduces down to x squared minus 9 is 0. And there's 3 friendly methods for solving something like that. You can just throw the negative 9 back over to the other side, take the square root of both sides, and critically remember that there's a plus or minus that you've got to bring because negative 3 squared is also 9. This one brings you back to previous or prior learning, where that's just the difference between perfect squares that factors and actually confirms that there's a plus and minus 3 in play. That's why there's 2 answers there. And then one could also just say, what about the parabola y is equal to x squared minus 9? That actually just translates the x squared, drops it down 9 units, and picks up zeros at 3 and negative 3 when you're trying to find the zeros. So you've